Okay. So heuristically, what's happening is the following. You know that this is a periodic function, right? It is a periodic function whose period is, commensurate with L, right? And this is also a periodic function. If n is, is an integer larger than L1, then of course its period is 2L, 3L, sorry, L by 2, L by 3, L by 4, or, things like that. So the idea is that, all these functions are periodic in L, right? So what the idea is that any function that is periodic in L can, if it's nice enough, it can be expressed as a sum of these basis functions, which are also periodic in L. Okay. So the idea is quite simple. So, before I go and talk more formally, let me just, discuss some examples. I mean, I'm just making this up, so this may not be the perfect example. Suppose you have a signal which is like, a square wave. Okay. So periodic signal, which is a square wave. So let's take, so this is f of t. So instead of x, we're using t here. So the idea is that how are you going to, is there a way for you to be able to approximate the signal? Well, a very crude approximation would be to use a sine wave, right? This would be a very crude approximation. And what the Fourier analysis is telling you is that you can improve this approximation by adding more waves. So suppose you add to it, so this is not a sine wave, a cosine wave, but you know what I mean. So you can add to it, say, a wave like this, which has a smaller, a smaller amplitude. So, and now if you add these two waves, then you will get something which is like, something like this. Sorry, I'm not going to be very, it'll be some distorted version of the square wave. And the idea is that by putting in more higher and higher frequency of waves with the correct amplitude, you adjust the shape such that in the limit where you have an infinite number of waves, the sum becomes a good approximation, a very good approximation to this, to the original wave, okay? So this is a very heuristic interpretation of the idea behind the Fourier wave. Okay, so it is not something very like it is actually quite intuitive, but of course the details can be quite mathematical. Okay. Okay, so let's write down some words. So as I said, the constants an and bn are called the Fourier coefficients, and the functions cosine of 2n pi of x over L and sine of 2n pi x over L, they form a complete basis set of like basis functions. Sorry. For any periodic function that satisfies the Dirichlet conditions. Okay, so the magic is in these coefficients. These coefficients control how much of these functions you add to the mix, right? So if I give you, if you know this function, so I give you this function, but you have to model it in some Mathematica or something, then you need to find these coefficients. So you know this function, either numerically or analytically, and you have to find these coefficients. How do you do that? You do that by using the following orthogonality relationships. So for example, if I take a cosine function, so 2mx pi divided by L, and say sine of 2n pi x over L, and integrate it from minus L by 2 to plus L by 2, and just for good measure, I divided by 2 over L, then you can show that this is 0, right? This is something, it's quite easy to show. So I hope you are able to show this, right? So you should be able to show this by this point in your life. Okay. And, you know, try this, okay? And then we also need the following orthonormality condition. If instead of having one cosine and one sine, you have, say, two cosines, but the integer is different, then you also have 0. But if the integer is not different, but same, then, you know, the normalization here tells us that this is going to be 1. So this is equal to m delta mn, where delta mn is the Kronecker delta. Okay? Delta mn is 0 when m is not equals to n. It's 1 when m is equal to n. So this is another relationship. And similarly, we have the relationship that if instead of cosines, we have sines, so sine of 2n pi of x over L, sine of 2m pi of x over L, d of x, that also gives us mn. Okay, so these are the three orthogonality relationship that we use. And by using this, what we can do is that we can multiply both sides of the Fourier series by some function like this and integrate it, and depending on what function we multiplied with, that coefficient comes out. All the other coefficients go to 0. So we get the expression that an, this n includes 0, 2 over L, integral from minus L by 2 plus L by 2, the function phi of x cosine of 2 n pi of x over L d of x. Okay, so this is the expression for an. Similarly, for bn, we get 2 over L phi of x instead of cosine, we get sine.
Sir, is it like uh, have the have the series and we are finding out an and bn, or are making the series from an and bn, or
It's
both
equivalent.
ways are
Yeah,
possible?
both is possible. Yeah, that's very good. Yeah. So you can think of an and bn as projection. An and bn are projections of the vector or the function f of x, onto the cosine and sine directions.
The Fourier series is compared with a circle. Could you please explain that visually, I guess?
Yeah, the Fourier series, basically, it means that often in mathematics literature, the Fourier series is, it's basically, it's a map from, say, it's defined to be yeah. Okay. Well, yeah. The idea of a circle is because when you get identification, when you get a periodic system, right, with period L. So this is L. What does this mean? This means that you are identifying this point to this point, and that point to that point, right? So topologically, this is equivalent to a circle, where, so if there was a function like this, then on the circle, sorry, it's a very bad representation of this function, okay? So do you see why it's a circle, why the periodicity is equivalent to a circle?
Yes, sir.
Yeah, it's just, in terms of, topology, S1, which is a circle, is R divided by Z. Okay?
Okay.
Z is the lattice of integers, where what you're saying is that all the points which are translated by an integer are identified, and topologically that is a circle.